Welcome to ELIC124, Computer System Fundamentals. This will be Lecture 9 on arrays and pointers. As you can see here, in my setup, I will be dividing the screen in half. On the left side, we will go through the lecture notes. You will all have a copy of these notes, exactly as they are shown here. And on the right side, I will be writing code, and you will have a copy of this code as well to run. Okay? So let's begin. So let's start with the basic definition of an array. What is an array? So an array is defined as a series of objects. These objects are all grouped together and they have a common name. The only difference between each one is that they have an index associated with it. Each one is differentiated only through that index. Otherwise, they look all the same. And arrays in particular are very useful for storing related objects. Related means that you have multiple instances of something. For instance, grades or classrooms, textbook numbers, credit card numbers, they're all related, right? And in particular, they're very useful to use with for loops. Whenever we have a for loop and we use the counter variable, we can use the counter variable in the array as the index, and we can loop through an entire array like this. Okay, so let's go through and just have a quick example of declaration and usage of arrays. As you can see, to declare an array, we utilize the square bracket notation. So here, this is the declaration of the array. Let's go ahead and use the array. To use the array means we utilize the values in the array. So remember, there are 3 elements in this array, and we can go ahead and utilize each one separately. This one is the first one, this is the second one, and this is the third one. As you can see, the only difference between them is this index, which we have to tell the compiler which one we are talking about before we want to use it. Okay? Printing each element of the array is the same thing, right? We utilize this just like we would any other variable. And so we print them separately. So let's take a look at some of the syntax here for a minute. As you might have guessed, the number that we put here in between the first 2 brackets during a declaration is actually just the size of the array. The size of the array is also the total number of elements. That means there are 3 colors in this case. And when we utilize it, when we use each of the colors, the bracket here tells us which one we want to use. So as you can see, they look the exact same in syntax, but this is very distinct from this. The number that we put here is more commonly referred to as the index. That's a term that you should know, and it's utilized by pretty much everybody in the industry. And as you can kind of see here, arrays, the first array element always starts at 0. It doesn't start at 1. Okay? You'll be actually familiar with this if you've done any other programming in any other languages. But some languages, like the proprietary MATLAB language, actually likes to start their arrays at 1. There is good reasoning for starting at 0, and there's good reasoning for starting at 1. But modern languages, like C, they will all start their arrays with index at 0. This is what's called zero-based indexing. And the last element will be n-1. So as you can see in the declaration, we have 3, and the last element will be 2. So 0 to 2 inclusive. That's very important. A natural question you might ask is, well, what happens if we try to do something silly? For instance, this. Okay? negative, positive, doesn't matter in this case. This will now be what's called out of bounds. We cannot write to the fifth element in this array because we only have 3 slots to put them in. You can think of them exactly like containers. You have 3 containers and you're trying to tell the computer, hey, can you please go to container number 5 and put the number 5 in it, surprisingly. This will give you an out of bounds. The out of bounds actually happens in the reverse way as well. For instance, this will give you also an out of bounds error. Okay? Any out of bounds error in arrays in C programs will cause crashes. Now, most of the time, if you are debugging your program, you'll get a nice little error that says out of bounds. Okay? For release programs or for programs that do not have the debugging information embedded, you'll just get nasty segmentation errors and I/O errors, things like that. So generally, we don't want to do this. We want to always make sure that we are within 0 to 2 inclusive. And just a small little point is that an array is actually just a pointer in disguise. Okay, we will come back to this when we look at pointers. We'll see how this array is just a pointer in disguise. So now let's take a look at the difference between array declaration and array initialization. From our familiar standpoint, we can always declare an array anywhere. Here we declare an array called sample with 4 elements. Okay, nothing too complex so far. Next I will show you exactly which elements are out of bounds and which elements are okay to interact with. For instance, elements whose index start with 0 all the way up to 3 inclusive are good. Anything -1 and -2, -3, or 4 and higher is considered out of bounds. So this right now is just simply array declaration followed by some sort of array usage somewhere down there. Next we can look at the difference between that and initialization. So here now we initialize an array called other with again 4 elements. Now mind you, the different syntax here is to show you exactly how to initialize that. We put all of the values we want, all 4 of them, in curly braces separated by commas. And we give a nice big equal sign here to the array. This will tell the compiler that, hey, I want to initialize this array having values 4, 9, -1, and 0. And we can do similar operations with this array as well, right? We can add parts of the elements to each other. We can multiply them by other things. We can do whatever we want. Treat them exactly like they are double variables all by themselves. So let's take a look at some common pitfalls that I see very, very often with arrays. And that is the usage of arrays without an index. Now, I've already told you that arrays are pointers under the hood. So what does this have to do with using an array without an index? Well, it turns out that if you use an array without an index, it is actually just a pointer. So here's a quick example to show you exactly how that works with our previous example. In this example, we gave colors, which is this array of 3 elements. We gave each of them a number here. And we try now to make a modification that we want to print colors. Well, as you can see here, the old code is here commented out. That's what we should do. This is what you should not do. So when you put colors just by itself here, it doesn't actually print all 3 in the first %d, right? The %d is a single number, not 3 numbers. When you use colors like this is valid syntax, but it has a different meaning. This will actually just give you the address of the first element only, which is the same thing as just writing colors. This is a small trick which you can do. So the address of colors at 0 is the same thing as colors. Okay, so as you can see, because it's an address, that's not what we really want, right? It doesn't print any values. It only prints the address of the first element. And because we don't know where the computer will store this array, this address is pretty much meaningless to us to use. We can't use it in any, meaningful computation. Okay? So going back, we can easily pair loops and arrays to work together. As I've told you before, the counter variable I in a loop is very useful to actually index an array. So for instance, let's say we wanted to change the entire array, right? We can write some code here that will do so. Let's first get rid of these out of bounds because we don't like those. And let's go ahead and make a bit of code that naturally clears the entire array. We can start with our familiar for loop here. And now we can just go ahead and put sample at I and just say that equals 0. Now what this code will do is have the following effect. It is the same as saying sample at 0, sample at 1, sample at 2. All of that is equal to 0. This code and this code is now the same. So as you can see, we've modularized the code a little bit here. We've shrunk it down to be more expressive. Okay. One particular thing which you might notice is that I put the number 4 in here. Okay, that's because we know that this array here is actually what's called a static array. We know the size of it. So therefore, we could put it here in the condition for the for loop. The inverse of a static array, or the other case, is what's known as a dynamic array, whose size can change during the execution of the program. This array here, because it is static, cannot change during the execution of the program. Dynamic arrays we will get to as well when we study malloc. This will be part of the last lecture that we do. So hold all questions about dynamic arrays until then. So let's go ahead and actually write a small sample program. So I'm asking you here now to create a program that asks the user for 5 integer numbers in a row and then print the sum of these numbers. Okay, well, what do we need? Well, if I'm asking you to print something, you need printf. Okay. If I'm asking for user input, I'll need scanf. And then I will need an array of size 5 in order to store all those numbers. Right? So let's go ahead and start from our familiar stdio int main and return 0 at the bottom. Right? Everything crystal clear so far? We can go ahead and declare the array first. This will be called user's numbers because we want the user to input numbers and we want to store them in this array. I see. So we need to ask the user for user input. Aha. Okay, well, let's tell him, please enter 5 numbers. And now we can use a quick loop here to ask the user to enter which number, starting from 0 all the way up to 4, and then input that into the scanf. So as you can see, now we are loading up the array, each element of the array, with one of the user's numbers. See? So these are all related entries. All the input that the user gives you, they're all related in some sense. We want them all, and we want to store them all. Proceeding similarly, we can go ahead and add up all the elements in a similar way. Let's give a quick local variable here called int sum equals 0. And now try to reiterate over the whole array, adding each element of user number to sum. And finally, we can print the result. The code that you see here will also be made available to you for download, so you don't have to worry about missing it. Okay, let's proceed. What does it mean to take the size of an array versus, for instance, the size of an element? Are these two things the same thing? Probably not. What about array indexing? We already looked at this a little bit. The indexing is just giving an integer value into the square brackets, and it identifies which array element you're talking about. Passing arrays in and out of functions we will talk about shortly. And if an array is not indexed, what is the value? We looked at this. Please refer to the pitfalls slide for that. What is the relationship between arrays and pointers? Hint, hint, they are kind of the same. And what is the following syntax here? What does this mean? Why is it useful? What is the consequence of this? I'll leave that one for you to discuss. So let's have a quick introduction to pointers now. Pointers are simply integers. And this integer number is really just a container number. So when we ask the computer to find out what is the container number or what is the address of a variable, we're really just looking for the container number. Where is it being stored in memory? Right? The container number is just a nice way of not actually saying memory address. It's more like an abstract container. Each container, each memory address has a label, an integer label. And when we store variables of pointer types, we are really just saying, okay, we're going to store now a special integer that is a memory address. And there are two associated operators to deal with pointers. These are very, very helpful, and they are known as the address of operator and the indirection or the dereferencing operator. They're best summarized by this graphics here. So anytime you have a variable, we can always get its address by following this line here and using the ampersand operator here, which is known as the address of operator. And that actually changes the type of variable from int to int star. Anytime you see a star, that's telling you that you have some sort of pointer here. It is a memory address to an integer. It is not an integer that can be used wildly in arithmetic and such, like this integer on the left. It is a memory address integer. It's not meant to be used like that. That's why it has the star in there, to indicate that. And if we have a variable that is of int star type, we can always ask the computer, hey, can you please go to that container number and tell me what's the value stored in there? And we could do so using the star operator in this case, or the dereference operator, or the indirection operator. So we can follow this back to the variable itself. That loop there should be hard-coded in your head. We'll be using this quite a bit. So we can use the address of operator to get the memory container number of any variable, and we can use the dereferencing operator to reverse this process, right? So what can you tell me about the address of and the dereferencing operators is that both of them combined, they are inverses of each other. Just like how square root of x and x squared, they cancel out. The address of and the dereference operator, they cancel out as well. So let's take a look at a quick example, starting from our familiar standpoint with stdio, int main, and return 0. Let's just go ahead and declare some integer x somewhere. Okay, we don't know where x is stored, but we can always ask the computer, hey, can you please tell me where that is being stored? And we can do that using this ampersand x, and I just put brackets around here to show you the order of operations. So we first have to evaluate ampersand x, means get the address of x, and then store that into my address. As you can see, my address has a type int star. Not integer, even though it is an integer under the hood. It's typed as int star. Okay? We can go ahead and actually print that. We can print what's the memory container number, just like you would any other integer. The only caveat, or the only difference, is that when we print a pointer or a memory address, we are really just using %p instead of %d. Not a big difference. Even if you used %d or %u, probably it'll work. But customary to use %p. We can reverse this process using the dereference operator, right? So let's go ahead and take the my address as a variable that we know is a int star and perform what's called dereferencing on it. So we do star and my address, and again I put brackets here for brevity so that you can see what's happening first, and then assign that into another variable. So whatever value that is stored at this memory address is somehow going to be now copied into this new integer original value. And we can confirm that by printing its value. So let's go ahead and do that here. So it tells me here x is stored at 133FC50. Does that mean anything to anyone? Not really. It's kind of a random value. We don't really care. Okay? And now we can see that original value, which is the new variable, it also has a value of 10, exactly like how we started with x. So somehow we got the value of 10 from its container number. This is the container number. We look inside that container number and we can pull out the value 10 from it. That's what this does. Pretty cool, huh? So here's the quick verbal explanation of what happened in that program. We use address of to retrieve a memory address, and then we store that into my address. We use the %p format specifier to display its value. Note that when we use %p, it'll display it in hexadecimal. Not a big difference, just a peculiarity. And then we can reverse this process finally by using the dereferencing operator directly on my address. Whatever we get at the end is 10. We store that in a new variable called original value. And that's it. We go ahead and print that variable, and we can see we've retrieved x somehow through pointers. It's very easy to get confused when starting with pointers because there are 3 uses of the star in C. Okay, so both operators, the star and the ampersand, they are unary operators, so they must come before the variable. Okay, but there are multiple uses of the star. For instance, when you look at the multiplication of 2 integers, we can directly declare the product as 30 times 20. That star is multiplication. The next usage of star is when we have float star. Can you see that? And now we can go ahead and initialize some memory address, and I'm going to just put null here. We won't talk about that too much, but it just has a value of 0. And then the third usage of this star is here when we actually do dereferencing. Now all of these, they all look kind of the same, and they're very easy to get confused. Which side of the variable does star go on, right? Well, for an operator, it has to go before the variable. That's important. Float star is a type. That's why it's not an operation here. This float star is a type. Star point to float is an operation. So it has to come before the variable itself. That's important. Okay. So to really test your knowledge on pointers, you should know the difference between the ampersand and star operators. Right? We looked at them. They are called the address of operator and the indirection operator. You can also use dereference operator as well. You have to know what their difference is and what they do. Refer to that chart that goes in a cycle. That's very, very helpful to understand what's the difference between one and the other. Okay? Passing pointers to functions, just like how we pass array to functions, we will see this shortly. So I will skip that one for now. What is a void star? Ooh, that's a tricky monster to deal with. I'll let you take a guess at that. We know it's a pointer because it has a star, but a pointer to void? What does that even mean? Why would anybody want this in their code? That's a pretty interesting question. What is a char star versus a char bracket bracket? That's, oh boy, that's a big one there too. Hint hint, they're kind of the same. Hint hint. The next one is an int double star. If we know that int star is a type, what is an int double star? Initially, when I would read this, I would think, hey, double star, that's a pointer to an int. But why would we ever need such a thing? There are lots of use cases which I can think of that you have all encountered before, but you don't realize they are int double stars. For instance, if we know that an int star is kind of like an array, then an int double star, would that be an array of arrays? Another way to say that is we can use an int double star as a two-dimensional array. Pretty cool. How do we print a pointer's value? That's pretty straightforward. We use the %p. Okay? Remember that it prints in hexadecimal. And the fundamental question, what's the difference between a pointer and an array? And hint, hint, they are kind of the same, but hint, hint, there's some differences between them. They look the same. Moving on, let's talk about how do we use arrays and pointers in conjunction with functions. Specifically, we want to be able to pass arrays and pointers to functions just like any other variable. We will achieve this shortly. When we pass a pointer to a function, just a pointer, we are really giving the function a copy of the memory address. Remember that a pointer is just a memory address. When we give the function an array, we also are giving it a pointer. The pointer is actually just pointing to the first element of that array. So when we give any function arguments, the good rule of pass by value still applies. We talked about pass by value earlier, but to go over it again briefly is that anytime you call a function, all the arguments you give to the function must be copied and given to the function to operate with. In the case of a pointer, when we copy, we don't copy the value it's pointing to, we just copy the memory address. Similarly, for arrays, we do the exact same thing. We don't copy the entire array, we just copy its memory address, the first element's memory address. So let's look at an example of passing a pointer to a function. Starting from our familiar setup with stdio, int main, and return 0, we can go ahead and just declare a variable. We'll call it x, give it a value of 10. Next, I want to have some magic function that I'm going to write. We haven't written it yet, called double number. And the parameter that we give to double number will be $x, which in this case tells you that I want to give double number the address of x, the memory address of x. Okay, so let's go ahead and write that function. We know it's void because it doesn't return anything in the main code here. We know that. It has a int star as an argument. Remember, when we do $x, the type of this is now int star. It is no longer int. So when we pass it to the function has to admit or accept an int star. And we're going to name that variable here, that argument, target. And here's where the tricky part comes in. If we want to double the number, what do we need to do? Well, let's do something kind of cool. We take the memory address given to us here in target and we can dereference it. That means we will tell the computer, hey, can you please look where the container number of this is, and I want you to multiply the value inside by 2. Right? This here on the left hand side really just corresponds to the variable x. It's an alias for it. When we pass the address of x here, we always remember our rule for pass by value. We get the address of x and we copy it. We can copy it as many times as we want. Doesn't matter, as long as we're not copying the contents. So we copy the address and we give it to this function. Now this function can operate with that address. It goes to its container number, multiplies the value inside by 2. And finally, at the end, we can just go ahead and print the value. And if everything is good, we should expect that this will double the number. So let's go ahead and run this code. And indeed, we say we see that it is doubled is 20, exactly as we expect. If you remember in our previous lectures, when we were first introduced to functions, I had written a function that was also called double number, but did not use pointers. When we modified the value inside, multiplying it by 2, it did not have an effect on the outside variable. So let me do that value, that change here now. Going back to what we did before, it used to look something like this. As you can see now, we no longer give double number the address of x, we give it x itself. We give it x itself, which gets copied as a new variable, which also has a value of 10. Then we modify that changed value, we multiply it by 2, and then we exit the function and come back. In this case here, we can see that we will not be able to double this number. This is pass by value, and the previous one is what's called pass by reference. Anytime we pass data to a function using pointers or arrays, it is known as pass by reference. And this is because the function itself has a reference to some external variable. So in our example here, we have a reference here to the variable x somehow, even though x is not within the scope or the main body of double number. This applies to arrays as well, because as we've seen, arrays are really just pointers in disguise. And all of this really under the hood is still just pass by value. We're just now passing the memory location, not the value at the memory location itself. And when we pass arrays into functions, they are also passed as pointers. Now we know that arrays are sequential in memory, while a pointer is just a memory address of one element, right? So that distinction between them really doesn't matter when we are passing the actual memory address itself. We only pass one value. What the function does with the pointer, whether it interprets the pointer as just a raw pointer or as an array, is up to the function. And it is best described in the syntax of the function itself. And we can use various tricks to help us identify whether the pointer which we are giving to the function is really just a pointer to one element or a pointer to multiple elements, i.e. an array. So let's actually go and see how we would pass an array to a function in the following example. So let's start with our familiar stdio and int main setup. We can go ahead and declare a double array having 8 elements. And not surprisingly, we can load up each of those elements with some number. Okay, not a problem. Next, I want to create a function called findSum. And what we're going to do is we're going to give the function our array as well as the size of the array. And we'll see why that's important really soon. The output of this function should be another double, which in this case is going to be the sum of all the elements in that array. So let's go ahead and declare a function here called findSum. It has a return value or return type of double, and we can go ahead and automatically put double sum equals 0, and hopefully we can fill in the middle code here and then return sum at the end. Now it's very important to see that how we pass arrays is like this. We do double because the array will hold double values, and we use target here as the name of the array, and we put these square brackets here. Okay, I will show you in a minute how we can do this with a pointer, but let's just proceed for now. And we also give an integer value indicating the size of the array. So remember that because we are passing an array of size 8, we need to tell it of size 8 as well. The integer 8 is not carried with the array itself. We have to pass that separately. That's why we pass x here as the array, and 8 as the size separately. Next, inside of the find sum function, we can increment this sum value here by just adding up each of the elements of the array. We utilize max size in our for condition here. So we iterate between 0 and max size, and then we add up all the elements in that array whose index is I, that comes from the counter variable inside the for loop. And we added them all up and return the sum. And then finally, at the end, we can just go ahead and print the sum. Okay? So let's go ahead and actually use this, and we'll see what we get. Aha! 3.14159. Well, it kind of looks like I did 3.14159265535, whatever. Right? I just made a nice little number there so we can see that this thing is actually summing up all those entries. Let's modify the code and tell the computer only to modify, let's say, the first 4 entries. And we can do that as well. So let's go ahead and run that code. And, not surprisingly, we have 3.141. Right? If we were to do something bad, what we could do is we could tell it to add up 16 values in the array. Uh-oh, but look, our array only has 8. What do you think will happen when we run this code? Look at that. It actually did it. Whew, we got lucky. In normal circumstances, if you try to read out of the bounds of the array, i.e. read more elements than you are assigned in memory, you could encounter a crash. Now, for us, we got a little bit lucky and we didn't. But that's not a good thing to do. We should always have this number be the same as this number here. We always want to have the size be the same. So sometimes it's customary to do something like this. Let's make an int. We'll call this max size. And we'll give it a value of 8. And let's now give max size as the argument here. Because it's a const int, we can use it to initialize an array. And we can also give it down here to the function itself. This will make sure that whatever value that I use here is the same that I use here. So in this case, if I did 20, that's okay as well. We've only initialized 8 of them, but we have 20 spaces. That's okay. What it is not okay to do is initialize 8 of them and have, let's say, only 4 spaces. Or initialize 20 of them and have only 8 spaces. That's incorrect, all of those. So this is customary to do code changes like this. This is better code than just simply telling me it's 8, 8, and nothing here. This code here, this 8 and this 8 should logically be linked. That's where we can introduce the const int here and make sure that we give it to both the double array initializer and this one here for the function. This is good code. This is better. I want you to see next that what I'm going to do is I'm going to modify this code here. Let's bring it back to 8 elements since that's what the original code was. Let's change this now to be, instead of this notation, I'm going to change this target to be the following. I'm going to say double star. Now we remember that double star was a pointer. And yet, when I run this code, everything will be the same. So as you can see, I've changed notation between array notation here and pointer notation here. Mind you, these will do the exact same things. That's why an array really is just a pointer in disguise. So we can write it in this way or in this way. However, I reserve this for actual array usage, while I reserve this for actual single pointer usage. Single pointer in this case would be like if we had only one element, or if we had, for instance, double and let's call this y equals 50. Okay? And if we had that and we put y in here, that would work as well. Now, I'm going to do one thing. Y here is a single value, and as you can see, IntelliSense is telling me there's something wrong here. Y is of type double, and again we need to take the address of, and that will work. Now, why didn't we have to put address of here when we used x? Well, remember that x is really just the same thing as the first element, address. So this is a shorthand notation for this. Oops. Okay? You have to know this difference here. So when we pass x, we're really just saying it's an address. So there it is. It's the address of the first element. Sometimes, if you like, you can put these little brackets around the 0 part to really be clear as to what's happening first, whether we're looking inside the array and grabbing the first element or whether we're taking the address of. But it is customary just to do this and then to simplify that notation from this syntax into this syntax here. Okay, that's basics of arrays and pointers, and you can see how this would now work. So let's get rid of this one, and this would work in just the exact same way. Let's go ahead and run the code, and ta-da, it will work. So there are two ways of writing these functions. To admit an array is really to say I can write it this way or I can write it this way. In both cases, I am really just receiving a pointer. Target, it's here, and here are both pointers. And when we pass the value, the pointer value, we can write just x. We don't need ampersand x here because the array itself is just a pointer. Pretty cool. So I've put down a few resources here that you can look at for more clarification and more examples and more description about arrays and pointers, as well as passing arrays and pointers to functions. And if that's not good enough, you can always look online on YouTube and Google. There is a lot of information on the subject because C and C++, which you'll probably find a lot of examples with, are older languages. So they have a lot of references and a lot of materials that you can go through if you need help. And finally, if that's not good enough, you can seek out both myself and your lab instructor for the for additional help. Okay, that concludes our lecture here on pointers and arrays and how we use them in general and how we pass them to functions. Thank you.